Solution concentration technology using mechanical vapor recompression, MVR, solves the problems of scale formation on heating surfaces and cleaning of secondary steam from aerosols. The technology is based on the use of innovative heat exchangers, drum film evaporators, DFE, and horizontal packed heat and mass exchangers. The animation of the modular evaporator plant shows 3 DFE modules located at the top and 1 horizontal packing unit, below, designed to clean steam from aerosols. After compression ends heating in the roots pump, the steam from the steam header is sent to 3 DFE modules. In the example shown, a roots pump of 500 kg/h compresses secondary steam at a pressure of 70 kPa to 140 kPa and raises its saturation temperature from 90 to 109 degrees Celsius. This allows to use this steam as heating steam in a DFE. Each DFE module includes a horizontal cylindrical body and an internally rotating evaporator drum. The drum at the bottom is filled with the evaporating solution. When the drum rotates, a film of solution forms on the inner surface due to wetting. When the drum body is heated from the outside due to the condensation of the heating steam on the inner surface of the drum, water evaporates from the film and secondary steam is formed. The module of a horizontal packed mass exchange apparatus located in the lower part cleans the contaminated steam from aerosols. This module contains a drum packing device, the lower part of which is immersed in reflux. Purified steam from the module with a rotating annular bed of nozzles is fed through the steam pipeline to the roots pump, where it is compressed, heated and the cycle is repeated. The heating steam condensate formed on the outer surface of the drum flows into the lower part of the DFE housing. The hot condensate discharged through the thermodynamic steam trap is sent to the heat exchanger, where it transfers heat to the initial solution entering the DFE modules for evaporation. Thus, the solution enters the DFE modules already heated, which allows to increase the efficiency of the evaporator plant. When evaporating solutions with surfactants, foam may form. When the foam bubbles are destroyed, aerosols are formed that pollute the secondary steam. The module of a horizontal packed mass exchange apparatus located in the lower part cleans the contaminated steam from aerosols. The solution level in the drums is automatically adjusted using float valves. The evaporator allows the concentration of solutions to high salinity values, at which precipitates and colloidal particles begin to form. It is colloidal particles in contact with the heating surface that gradually degenerate into solid layers of scale, which impede heat transfer. To prevent the formation of deposits on surface, the heating surface is constantly cleaned with a rolling rod with a spiral wound. If it is impossible to move this rod in the axial direction, the spiral winding works like an auger, which not only cleans the resulting sediment particles, but also transports them to the concentrate discharge point. This prevents particles from accumulating in the concentrated solution and makes the evaporator resistant to scale formation. The nozzle device is a rotating annular layer of nozzles located between 2 perforated shells. Polluted steam entering the central part passes through a rotating layer of nozzles and is cleaned from aerosols. The nozzles polluted with aerosols during the rotation of the annular layer are periodically washed by the circulating reflux and are cleaned of contaminants. During condensation and evaporation, heat transfer is very efficient, but the presence of non-condensable gases can drastically reduce that heat transfer during condensation. To prevent this phenomenon, It is possible to periodically discharge to ventilation the gas-vapor mixture when the electromagnetic valves are opened for a short time. The presented evaporator concept was developed primarily for the processing of liquid radioactive waste, but can be used for many other purposes. When processing LRW, it allows to obtain a concentrate of optimal salt content for cementing and clean non-radioactive water.